Hi everybody, my name is Umit from Stony Brook University. I'm going to talk about our work in machine learning framework to improve storage system performance. The number of tunable parameters in 4.1951 Linux kernel is over 1,000. There are parameters which are related to most of the Linux kernel components. Here are a couple of examples of them. The first one is read add size. Reader is a storage prefetching system. Its main objective is to improve I/O performance by caching future storage data based on the tunable per disk and per file read ahead values. The second one is I/O scheduler. We can change I/O scheduler based on our workload needs, like low latency or high throughput. Yes, there are so many tunable parameters in the kernel, but why are they so important? Because they can affect performance and latency drastically. By tuning these parameters, we can gain so much performance. Do the default values or a single value work for all the time? Because if that's the case, we can benchmark the system and tune it once. The answer is no. There is no single value that works for everything. They are highly dependent on the workloads. As a first stage of our research, we mostly focus on the I/O subsystems, because if we tune parameters for I/O subsystems correctly, we can enhance I/O performance a lot. Since we cleared out why tunable parameters are important, now we have to figure out how we are going to adjust them. Can we adjust these parameters manually? The answer is yes. But as I mentioned earlier, there is no single value that works for everything, and then they depend on the workload types. That's why the tuning manually only works for a unique setup. If the manual tuning works for a unique setup, still, can we tune once and just leave them? This is possible, but not applicable for most of the times, because either the workload that we adjusted the parameters will change because of the software development or other things, or we will start running different type of workloads on the system. That's why we have to adjust kernel parameters dynamically. Even though we need to adjust these parameters dynamically, can we tune these parameters with a simple algorithmic techniques? No, it is not that simple, because there are thousands of parameters, and then tuning these parameters requires certain expertises. Plus, all these parameters are interdependent multivariables. We would like to do multi-objective tuning as a future work in our research. Because of all these reasons, we propose a new approach, which is KML, a machine learning framework for operating systems and storage systems. Now, we are going to go through the KML design principles. In order to make the KML work in kernel, we had to implement most of the mathematical and matrix operations from scratch using approximation algorithms. For each layer type and loss functions, we implement the function for forward propagation and another for backward propagation. We perform inference by creating the computation-directed acyclic graph of the individual layers. We compute gradients using the reverse mode automatic differentiation. Operating systems are sensitive environments where the precious CPU and memory resources must be carefully managed. Therefore, any machine learning implementation inside the OS must be efficient. Most of the operating systems disable floating point operations in kernel to reduce the context switching, overheads, and then also unwanted exceptions. There are techniques to do floating point computation without the floating point units, like fixed point representation and quantization, but we used Linux kernel's native approach for enabling and disabling floating point unit in the kernel. We minimize the number of code blocks using floating point operations to reduce the number of context switches that would also have to save and restore floating point registers. We achieve this using asynchronous training. You can find more details in this paper. We designed KML to be as efficient as possible. We used log-free circular buffers to process and asynchronous to train on the input data. Since losing part of the training data could reduce the neural network model's accuracy, users must carefully configure the circular buffer size based on the sampling rate of the data collection. As we all know, kernel programming is challenging. We designed KML, the development API, to abstract away the external functionality. In this way, KML can be compiled both user and kernel space with an identical behavior. Users can collect the data using the KML data processing and normalization components, then train on the ML models on collected trace data in the user space. Other adjustments, such as trying different neural network architectures or hyperparameters, can also run in user space. When the neural network model is ready to be deployed, the user can save the model to a file, then load the neural network model with a given path to the deployment file in the kernel module. You can see the execution flow of the read-ahead use case on the right. User space training and kernel space inference is very useful, for sure, but we still support in-kernel training. There are two critical reasons why we support in-kernel training: performance and accuracy. One of the most crucial parts of the machine learning flow is collecting the training data. That's why getting accurate data from the kernel without any overheads is very important. In kernel training also allows operating systems developers to build machine learning solutions using reinforcement learning. Using reinforcement learning, we can build machine learning approaches that can adapt themselves based on the feedback from the system. KML also ensures the inline data collection operations from the KML and then do not cause any deadlock. KML uses slug-free data structures to avoid deadlock and to reduce the overhead of the data collection operations. You can find more information about this topic in the paper. We choose the read-ahead problem as our use case. As I mentioned earlier, read is a storage prefetching system. Users can provide the hints to the system through the system code such as fadvice or madvice. Our goal was to replace these manual or programmer-driven heuristics with an automated ML technique that quickly adapts to changing workloads and tune the read-ahead values as needed. We studied the read-ahead problem empirically. We tested DrugsDB with the 4 different workloads, 20 different read-ahead sizes, and 2 different storage media. We then built mapping from the workload type to the read-ahead value that provided the best throughput. The results show that there is no single value that maximizes the throughput for all the workloads. Moreover, the relationship between the read-ahead value was not linear and at time exhibit long tails. As you can see, read random workload on NVMe example on the right. X-axis shows the configured read-ahead sizes and y-axis the operations per second, which is the throughput. 256 was the default value for the read-ahead size. As you can see, the 256 is a suboptimal value for the read-ahead. In order to build our neural network model, we need to collect training data. We collected training data from the Linux kernel using trace points. These trace points track the file back pages. We used our own tool, Reanimator, to accommodate mmap-related trace points such as add to page cache and write back to page. In the read-ahead model, we process the collected data points every second and then extract the features at the runtime. We tried a total of 8 features, which we selected based on our domain expertise. We then experimentally narrowed them down to just 5 features that had the most predictive accuracy. Also, we confirmed that using Pearson correlation analysis. You can see the list of these 5 features. We designed our read-ahead neural network as a multi-class classification model. Our model has 3 layers, and these layers are connected with the sigmoid activation function to model the nonlinearity exhibited by the read-ahead versus throughput curves as we investigated in the previous slide. We use the cross-entropy loss function and optimize our neural network using the SGD optimizer. We trained on the data that we collected by running the only 4 workloads on NVMe. We picked these training workloads because they were sufficiently diverse in sequentiality versus randomness. We measured the performance of our neural network using k-fold cross-validation with the K-stan and found that our model reached an average accuracy 95.5%. Our evaluation goals were to prove that using KML and building the ML-based solutions inside the OS can offer more generalizable and adaptable solutions than aging heuristics, and hence improve performance with a minimal overhead. The red line in the middle of the graph is the line for 1x, which means anything above the red line shows the improvements. X-axis represents the workloads and y-axis represents the performance improvements. To prove that our neural network model can learn abstract patterns, we tested our model under the workloads we trained on, as well as never seen before workloads that include complex mixed workload like a mixed graph. Moreover, while the training workloads on run an NVMe, our evaluations tried to dose and new workloads on an SSD. The results show that the read-ahead neural network can reach up to 2.3x better performance. Only for the read sequential on NVMe, KML actually lost 4% performance. All the other workloads are improved. This is because the read sequential maxes out the underlying hardware throughput, and then there was a very little opportunity to improve throughput. KML's attempt to learn and optimize read-ahead only interfered with the already optimal throughput. Figures show that how read-ahead neural network changes the read-ahead size during the DrugsDB's workload running on an NVMe device, and how the performance improves overall. These 4 workloads, read sequential, read random, read drivers, and mixed graph, running actually back-to-back. For an entire execution, performance improvements around 40%. You can see the read ahead size on the Y2 axis, which is represented as a transparent green, and throughput on the Y1 axis, and an X-axis represents the timeline. We ran the same benchmark 15 to 50 times and averaged the performance improvements. Figures show that there are fluctuations on the read ahead size tuning. The reason for read random and mixed graph fluctuations is that we clear the cache after every run, and then when the benchmark starts, read access patterns are different than the rest of the execution. And for read sequential and read reverse cases, fluctuations happen because of for time to time, these two workloads are quite alike each other. Even though because of the mispredictions, fluctuations happen, as you can see, we can still improve performance. In conclusion, operating systems and storage systems are evolving to support an ever-diversifying range of the devices and workloads. For best performance, storage systems need to optimize for specific workloads and devices. Our preliminary results show that for read-ahead case study, we can improve I/O throughput by up to 2.3x with a negligible overhead. We plan to apply KML to other storage subsystems like I/O schedulers, storage networking, network file systems, and page cache. We are expanding KML to support other machine learning approaches like reinforcement learning, which can solve certain problems better than classification approaches. We also plan to extend our neural network architecture to support direct last cyclic graphs, which can fork and join. And here is the end of my presentation. Thank you so much for listening.